Thanks a lot, everybody, for being here. Morning for you, evening for me. So I was mentioning earlier to Darby, so this is work that I've been doing mostly in my time in California before I moved to Germany. Essentially, so on stochastic integrated fire neurons and synapses, and a work that I really like because it has a beginning and almost an end to it, which is pretty rare. Right, so here we go. Okay. So the topic here is what was really driving some of my research at the time, is to understand how we can do probabilistic inference, a little bit like how the brain does it. So our brains do probabilistic inference. In fact, it does it in a unconscious way. So on the left there, you have the famous figure from Helmholtz, where you either see a rabbit or a duck, right? And which one really it depends on some kind of stochastic procedure. You have only some mild control over it. So that's anecdotal, but on the right, there's a more quantitative study and the integration of uncertainty in a Bayesian manner. So here the subject is trying to basically to make a motor action. And the two cues are given, so one visual cue and one proprioceptive cue with different uncertainty, so different variances. And what the authors here found is that the motor action then combines these two uncertainties in a way that is expected from Bayesian inference. So we can say here that the humans implicitly use Bayesian inference. So the question is then, how can we actually implement this, since we're interested in building these chips, as Darby told you about what I like to do, and I hear also this is the kind of things that you like to do over there. So what are the strategies here? So we can think of at least two strategies to compute to do probabilistic inference. So essentially, what we want to do is to compute the probability distribution. In this case, I'll give you an example. This was from the paper of Fisher in 2010. So what we try to do here is to find the joint probability distribution of two random variables, y1 and y2. So in the left case, this is done using so-called population coding. So essentially what you have here is a neuron which is tuned for so actually several neurons that are tuned to the different values that y1 can take. And so through a population activity, then you could encode this probability distribution. So this is a standard approach that's used also by Deneuve, and so some of the work that's been done in that area in the past decade. Here, in order to encode the two probabilities, we would combine two such populations and look at their co-activations, which would give us then this 2D density here. Another approach of doing it is instead to sample these values of y1, not to represent their probabilities, but just have some instantaneous firing rate, or maybe even a spike, whose probability corresponds to the probability of y1. And by plotting these samples of y1s and y2s, essentially we can sample from this 2D distribution. Now, what you can see here is that the right one is potentially more efficient, right? If we can do this, for example, with single spikes, we'll need 2 neurons for doing it. As in the left case, we actually need a whole bunch of neurons in order to compute at just represent one random variable. And so most of this work that I'll be talking about, actually all of it, is really pursuing this idea of neural sampling to represent these probability distributions. But of course, it raises the question, so how can I actually get these y1s and y2s to actually have a firing rate or activation that is consistent with that probability density? Okay. So the approach that we're taking here is that we assume that neurons and synapses are noisy, and this is actually something that's been observed in the brain. As the title indicated, we're going to be very interested in this synaptic noise and the fact that synapses have a probability of transmitting an event or not. In fact, the higher you go into the cortical areas, the more stochastic it becomes. In fact, here in the cat cortex, you see that the probability of release, in fact, that there is a transmission is close to 50%. So if you see this as a Bernoulli random variable, it's the most variable that you can get. And interesting, this work here on the left by Atwell also shows that there is a energetic reason why one may want to do this, and possibly also information theoretic view of why one would want to have stochastic synapses in neurons. So then I'm going to start here with some basically theory of stochastic neural networks and how we go towards building networks of both integrated fire neurons and non-integrated fire, so just conventional neurons, to do this probabilistic sampling. So just as a disclaimer here, this is one type of stochastic neural network, the Boltzmann machine. There are other ways of doing stochastic neural networks, for example, by doing Bayesian, using Bayesian neural networks. We haven't explored this, so this really starts with the Boltzmann machine idea. So in the Boltzmann machine, what you have is a stochastic unit here, here represented by the z's, and the probability of the z being equal to this exponential of some energy function here, and the energy function is the same as in the Hopfield network. Essentially, a Boltzmann machine is like a stochastic Hopfield network. And the reason why it's stochastic, one thought of adding noise, is that it's potentially something that can help escape local minima. So on the Hopfield network, you would have the step function, whereas on the Boltzmann machine, you have typically this this smooth activation function here, which is given by a logistic function. In terms of learning, because of course we're going to be interested in learning these distributions, in the Hopfield network, the learning is simply given by a single shot Hebbian rule here. So basically looking at the correlations between two neurons, average over the data. So that gives you the weight change. In the Boltzmann machine, you need to do learning a little bit differently, in that basically you have the same Hebbian-like unit and another one which corresponds to some kind of reconstruction of the data. So this is like putting the energies on the on the provided data low, where the data points are. And this term here is essentially to increase the energy around those data points. So this way you can basically build an energy profile that has minimums around the shown data samples. Okay. So how can we do this with spiky neurons? That was at the time, our goal was to build really spiky neural networks that could implement these Boltzmann machines. Here we took the approach of using probabilistic neurons, namely the so-called linear and nonlinear Poisson neurons. So they are equivalent models. So here on the left, basically have some a model where we have some linear filter with this corresponds, for example, to the PSP of the synapses, some linear integration, leaky integration, and linear integration of those PSPs, a threshold function, and some eventually some refractory reset mechanism. So we can also have a similar model that is consistent with this case. I should have added that there's also a noise term here. And this is called the linear nonlinear Poisson, which is, so we have the same PSP terms here, and some nonlinearity, which is then sampled using this Poisson approach. So there are cases where these two neural models can be equivalent to each other. The nice thing about this kind of model is that it's easier to think of it in terms of a stochastic process. And here, basically, you can say that the state of Z is given by the probability of spiking at some time, given the membrane potential here passed through this nonlinearity function here. And in the simplest cases, this is given by this function here, which basically has this exponential minus that same function here. Once we have this neuron, we can actually couple them together. So with these coupled filters, so saying we have the same neuron on top, same on the bottom, where we also have these post-spike filters that represent here the resets. And if we assume here a absolute refractory period at the neurons, which means that this probability is going to be 0 if the time between spikes between the last spike is smaller than some refractory period, and otherwise it's this mem n of v mem in this case here. So this nonlinearity I was mentioning in the earlier slide. Okay, so why did we do all of this? This is because there's some work showing from Wolfgang Maas's lab that if you have neurons that follow these dynamics, then they are guaranteed to sample from the Boltzmann distribution. And intuitively, the way that this works is, well, firstly, let's try to think of what does it really mean to sample in these spiking neurons. One way to interpret this is to say that at every point in time, a neuron is either active or inactive. And in Maas's approach, the neuron is active if it fired in some previous time window. That time window is exactly equal to the refractory period. So for instance, here we see that there's spiking. We have 5 spiking neurons here. This neuron and this neuron has spiked, and so we get the binary random vector 1, 0, 0, 1, 0. Okay, and so at every point in time, we can define such a vector. And what Maas's work is telling us is that under the constraints here that we have this probability function that's given by this exponential, as I was telling you earlier, and we have a linear integration. So it's not even a nonlinear function. So in this case, it's a linear function even. Then we are guaranteed to sample from a Boltzmann distribution. And what we show here is this with this equivalence between the leaky interunifier neuron and the LMP neuron, that's the stochastic interunifier neurons, such as those that we can have on hardware, can actually verify these conditions, at least approximately. Okay, so one thing that I didn't talk about here is where does that stochasticity come from? Right, so it's all nice that we can actually sample from this distribution, but at some point we need to implement these neurons, and we need to have a source of stochasticity. In the original work that we did, in fact, in the work that you're seeing up here, it's implemented as an additive noise. That was also the case in the previous slides, if you had noticed. But there are other ways of generating noise, and these are, for example, some intrinsic noise in the neuron, that the neuron somehow has some stochasticity, for example, in its conductances, which generates this internal noise. It can also be due to the synapses, basically, as we have neurons that talk to each other. As I mentioned, we can have these unreliable synapses, which create some stochasticity. Now, the output of the spike can also be unreliable, right? So the neuron may fail to emit a spike. Then there can be many reasons for this, and this really is typically modeled as a stochastic threshold. And the other method is to assume some sort of background synaptic activity. It's not really it's fair to say that background synaptic activity is noise, because it's actually, it doesn't tell us the origin of the noise. It's just some noise that's created elsewhere, and it's injected into these neurons. Now, it turns out that this background synaptic activity, so this is what we used earlier in our work, is typically implemented as some Poisson input. So another process that's stochastic is really slow to implement, and it doesn't even work that well. And so we were exploring different kinds of noise, and here we fell into basically to explore the B and the C. And in particular, for the stochastic synapses, we just assume that the synapses just fail to transmit, right? And we assume that this is the only source of noise. We wasn't really sure why this would work. And at that time, just by luck, there came an awesome work that showed exactly what we needed in order to pursue this idea. So this is work by Moreno Bote in 2014, where they showed that Well, the problem with additive noise, which is it's costly to implement, but there's also another problem that you observe, which is that you need to scale the amount of noise with the other inputs to the neurons. If the other inputs, which are not noise, for example, the signal, is much higher than the noise, your neuron basically behaves in an almost deterministic way. And that's what you see in this figure here. So this is showing the Fano factor. So Fano factor, if it's close to 1, the neuron is behaving essentially like a Poisson. The spike trains are Poisson. What you see is that as you increase the firing rate of the neurons, for example, by injecting noise, you see that the Fano factor goes down. So the spike trains become much more deterministic. But if you add stochastic synapses in a recurrent fashion, so the neurons are connected to each other here, in this case, excited in-between neurons, what you see is that this Fano factor remains equal to 1 over a whole range. And if you think of it, why would this be the case, right? There's actually really intuitive explanation. Firstly, if you've ever implemented a Poisson spike generation, you might know why. The efficient way of generating a Poisson spike train is just to take a regularly spiking neuron, just to remove spikes randomly, right? Now, this is exactly what these stochastic synapses and stochastic neuron firing is doing. It's basically removing these spikes randomly. And then that is being fed to itself, right? So it's basically every time it goes into the loop, it's removing more spikes and making it more stochastic. And this is how you can basically keep this Poisson spikeness to the whole range of firing rates. So what this corresponds to in terms of implementation is a very simple one. So you basically get that the neuron actually has some stochastic process at each synapse that basically lets the spike through or not. Okay. And what we did is now take the same ideas of Wolfgang Maas and sort of sample the Boltzmann machine, not by adding noise, but actually just by adding and removing these spikes. And so this led to the idea of the synaptic sampling machine, which is essentially something like a Boltzmann machine, where the noise was due to the synaptic effect. And with the advantages that actually this can be efficiently implemented in hardware, you only need to generate basically 1 bit of random bit per synapse and per spike. And we could use a learning rule that was also used for Boltzmann machines. A quick word about that learning rule. I mentioned it earlier, but this is an earlier learning rule called contrastive divergence, where you basically do is that the weight change is equal to the data correlations. So this is like a Hebbian term between population V and H. It's called V and H here because we were using restricted Boltzmann machines, so they had the visible layer and a hidden layer. But that doesn't really matter. You can generalize this to non-restricted Boltzmann machines. And basically what you do here for this learning rule is that you show the data to both V and this creates some activity on H, and then you increase the weights depending basically according to the Hebbian rule. And after some time, you let the network run, and so you get another V and another H, which is due to some form of reconstruction. And then you subtract the weight with this. You can show that this is what you need to do in order to implement this contrastive divergence rule. And this can be easily implemented with SDDP, just having these V and H neurons being connected to each other, basically implementing. So SDDP is basically a spiking form of Hebbian learning. And so what you do is that you apply the normal, so positive Hebbian rule here. So the weights increase as they spike together. And during the reconstruction phase, the weights decrease. So you basically just flip the sign. And this G here is doing exactly that. So in practice, the way that this looks as this, so we basically show the data, for example, a 3 here, and the weights are going up. And then you remove the 3, so basically going down here. And then you try to, during its reconstruction, you decrease W. And so you can just do this for every digit. At the end, you get some weights that can be, in this case, perform a classification classification network. The way that we did classification here was Believe me, this was more than 10 years ago, so we weren't working with very fancy data sets. It's just MNIST here. So we have a network that has these 28 by 28 visible neurons, a bunch of hidden neurons, and also visible neurons here that are the classes. Remember, a Boltzmann machine is a generative model, and so it's capable of doing unsupervised learning, but we're using it here in a supervised way by adding these classes. This makes it easier to assess how well we're doing. And at the time, actually, we were getting really good results, really competitive results in the 4%, 4% error. But what was really interesting is how efficient this was when compared to the restricted Boltzmann machine or compared to the non-spiking networks. So we compared 3 models here. So one RBM is for the restricted Boltzmann machine. So this is non-spiking, it's the traditional one from the 2006 paper. And the 2006 paper of Hinton. And then the S2M here refers to the neuron without spikes. So the activation is basically a rate, and S3M is a spiking version of this. I didn't actually really talk about the non-spiking version. We only use it as a tool to understand the math. And so what you see here is that it learns with much fewer samples. So these are the samples presented during learning. And so it needs easily like at least half of the samples compared to RBMs and much less compared to the non-spiking version. It was also fairly sparse, right? So this is the average activity ratio, is basically how many neurons were active at a given time step. And so that was lower. But and really interestingly, we had that this model required basically as many synops, even a little bit less synaptic operations compared to multiply accumulates in an RBM. Right? And given that a synaptic operation can be much cheaper than a multiply accumulate on the right platform, this was a very, very encouraging observation for us. Okay. So now this is there was one issue in the synaptic sampling machine that we just kind of talked about in the papers but didn't pursue further. If you look at the activation functions of these neurons in the synaptic sampling machine, you find that it's equal to this error function. So the error function looks something like basically a sigmoid function, so the logistic function, but it's not. It's a little bit different. And in fact, the logistic function is exactly what you would require in the Boltzmann machine. So we kind of thought, well, this is too bad, but maybe it's not. It's okay, and we just ignored it and just ran our learning rule as is, contrasted divergence there, assumed that it was a logistic function. And as you saw in the results, that actually works pretty well. But there's still something curious about this, which is that what you see here is, so besides the fact it's an error function, the argument here has a term that looks like a W times the inputs. So this would be something due to the inputs weighted rates. But it's divided by this term, which looks like something like a normalization, which itself is a function of this firing rate, nu. Okay, so what this means is that, well, you see, if I try to rescale the weights W, this is not going to change anything in the network, right? Because any scale is going to be canceled by this term here. So in this sense, it is something like a normalization term. All right, so that was our observations, and then we moved on. We had that paper, but then came another paper where they showed that actually that this term here, if you ignored this nu here, basically is very similar to weight normalization. Okay, so that's what put us on track for the other part of this work, which is called neural sampling machines. The names, by the way, weren't really well chosen. because the neural sampling machine, as I will talk about it in a second, also use stochastic synapses, but this is just how we call them in the paper. So that's where we are. Okay, so now we're coming to the neural sampling machines. What we did here is that we abandoned the idea of the integrative fire neuron because we wanted to have something that we could easily work with and also train using backpropagation. And so here we focused basically on neural networks, which were binary threshold neurons, and you'll see why we chose them to be binary neurons in a second. But that the only special thing in this network was that we had the so-called multiplicative noise. And that multiplicative noise can be thought of as the synaptic noise or as the neural noise. In the synaptic case, it's the same thing as we saw earlier. We have some presynaptic neuron that's then weighted by, so this is a weight matrix in the network, and then some stochastic synapse, which then just basically remove some of these spikes. And this can be very easily implemented by having, so these are real filters that were actually trained just by masking these weights with this salt and pepper noise on the weights. So here what we do essentially is that we forward pass on these essentially dropped out connections, and then we train on the probability distributions. So let me explain a little bit why we do all of this. So we focus here, as I mentioned, on a neural model that's a binary threshold neuron. Instead of using the classical 0 and 1, here we use the sign function. So basically a neuron that returns either +1 or -1, depending on the sign of u. And u we have here given by classical w times z, basically a weighted input, but then also multiplied by this c term here. Which in the case of the stochastic synapses is specific at each time, is different at each time step and different for every input and output neuron. Essentially, there's one per synapse. The only thing that we require here is that these C's are IID. Okay, in the classical example, these are Bernoulli noises. But what we can, before talking about the Bernoulli noise case, let's just look at the probability distribution of a neuron being active. Right. If we assume, because these are IID, the distribution of U is going to be Gaussian, and so essentially we're asking the question of what is the probability that a random variable distributed as this Gaussian is larger than 0. And that's simply given by the error function. In fact, the reason why we find the error function here is the same why we had an error function before with the leak integrative fire neuron. This error function has the arguments here of the expectation divided by this term with the variance. And in this case, we can basically, in the case of the Bernoulli noise, we can write this as follows. Basically, P here is the Bernoulli probability. A is some bias that we add to the probability here. I can explain later why we did this. And the variance here is given by this term here. Basically, it's the variance of the Bernoulli process here, P1 minus P and W squared. So we no longer see a Z here, or a Z squared, actually, that's what it should be, because we chose the neuron to be a sign neuron. Essentially, if you take the square of 1 or -1, you just get 1. And so in this case, we can remove this dependence on the input and have a variance that only depends on the weights. So if we do this and we choose basically arbitrary, we decide to choose this term beta as such, what we get is an activation function here, where we have some magnitude beta, a direction W, and basically the direction of this vector W, which are the weights of neuron I. And this is where, so essentially we saw that this was equivalent to a normalization approach. Before I go to that, just for some reason, my bullet point is all the way down. What we have here is that because we're actually removing spikes with this Bernoulli noise, as I explained, we also have an effect of regularization and dropouts or drop connects, which is also work that was published around that time. But we have this this essentially stochasticity that generates a reparameterization here of W, which acts as a normalization term. This was a paper that was from Salimans and Kigma. So this is the same Kigma from the Adam rule and variational autoencoders. And they in fact had exactly the same equation in their paper. This is the kind of thing that almost never happens in research, where you just write an equation and then a few months and years later, you see the same thing in a completely different subject and think, oh, maybe we can put this together. And that was exactly the case, actually. What was happening here in these networks is that they were doing this normalization of the inputs. And this was also happening in this spiking stochastic neurons networks, as I showed you earlier. But we try, this is something that we try to observe in these networks directly. And we did observe it. So what we're looking at here is a simple feed-forward MLP. And we look here at the activations at layer. I think this, if I remember, it's not indicated here, but I think it's at the first layer. So what you see is the activation, which is basically the U value that I had before, remains very close, basically unchanged through learning. Okay, and this is very different in the case of stochastic neural networks, essentially having additive noise. You see that this distribution changes a lot across learning. And so the reason why we have this in these neural sampling machines is really because of this term in the separation of magnitudes. I should have mentioned, I wasn't very clear, but what we did here when we were training these networks is that we were training both the beta, so the magnitude, and the direction, basically this term separately. And it's doing this, by the way, that has the effect of doing this kind of weight normalization. And the reason why I mentioned that we have this AI here, it was tempting to think that we would change the probability of a stochastic synapse, but it turns out if you change the probability of stochastic synapse, it changes the whole distribution. See, there's a dependence of P here, and we didn't want this. So we only wanted to change the effect of P in this expectation term, basically this term here. And that's why we added this AI here. And this was essentially like a deterministic version of the synapse that was coexisting with the stochastic version of it. In this way, we could train the two, essentially using the same rule as in weight normalization, this paper here. Okay. So this was a couple of years later, so we could actually work on harder data sets. So here we tried on MNIST and the CFAR 10s and N100s. We performed really well compared to the baseline, similarly or better compared to deterministic neural networks. These are, of course, networks that are longer to train and longer to do inference on because they produce samples. And for every inference, basically for every input sample, we had to create multiple stochastic samples to average and get these. In this case, we used 20 and 100. So you basically run the network 100 times compared to the baseline. So it makes them a little bit slower, actually significantly slower. The difference between BNSM and GNSM here is basically BNSM is for the Bernoulli network, and GNSM is for Gaussian neural networks. Instead of adding or removing the spikes at the synapse, you basically just corrupt them with Gaussian noise. Although this was not a spiking neural network, we could still try using spiking inputs. And so we did apply this to the DVS gestures, and compared to the other baselines that were not based on spiking neural networks, we were performing pretty well. Okay, so the final part of this talk is about their implementation, because we really were thinking of these neural sampling machines as models for implementation in crossbar arrays. And this was another lucky case with the group in the University of Notre Dame, where they were trying to look into stochastic selector units. So selector units are for memristive crossbar arrays, where you want to essentially have, in order to avoid these so-called sneak paths, where the current will flow across many different possible paths in the memristive array. I'm sure you all know what memristors are, but I'll just say it in case some don't. So these are essentially variable resistors, in which the resistance is dependent on the history of the inputs, and can represent, for example, weights in a neural network, or just the matrix in a vector matrix multiplication. So what can happen, because this is a resistive network, you can have multiple paths and so-called sneak paths, where a lot of the some of the current basically goes where the resistance is the lowest. And this is different with respect to what you would need in order to implement a proper vector matrix multiplication. Okay, so that's the problem. And the solution generally to this is to add a selector unit, typically a transistor. But this group was looking into selectors that were themselves based on some memristor-like effect, in this case, an insulator metal transition. This is a material, let's see, oops. Yeah, so this is essentially a material that becomes a metal at a certain temperature, internal temperature, and and is an isolator otherwise. And so it has this very high resistance if it's not on. And so we thought, so they were trying to use this, but it turned out to be really bad selectors. And here, when we told them about our work, that we actually need to have synapses that are noisy, they thought, wait, maybe we can use our really crappy selectors. And so in their selector case, in their hardware, what they had is that the thresholds of this of activation of these neurons could vary a lot. So that's the threshold distribution of the thresholds here. Of the selector units. Well, because there's a distribution there, we can basically assume that this is our stochastic process, and simulating these devices, which is pretty much behaves very much like an Ornstein-Uhlenbeck process. It has some history to it. We included this into basically the stochastic sampling, synaptic sampling as we had. They had a model where they had both the selector unit and another memristor, in this case a ferrofet, that was implementing the weight. So this, what we had here was really this combination of this, so stochastic synapse with a memristive synapse. And so we showed that this behaves in the same way as the neural sampling machines. And we really then here thought, so why would this be interesting as an application? And closing the loop with what I said earlier in this talk was about uncertainty. We want to implement probabilistic inference, and how can we get these neural networks to actually do this? And so we followed here the same approach as in the Yarin and Garamani paper. Which, by the way, we're also showing how you can use dropouts as a form of approximate Bayesian inference. And here, so what you see is that this neural sampling machine, or the simulated hardware, because we need to have several neurons here, which we didn't have in hardware, so we had to simulate it. We have this stochasticity, so really stochastic output as we change the input. Here, the input basically is the MNIST digit that's rotated across the x-axis here. So just basically run for different rotations. And what you see is that after a while, so you get this really high stochasticity on the output, which essentially reflects some sort of uncertainty. In a non-spiking network, you would not observe this, right? Because basically you just do the classification based on the softmaxes. There's one caveat, though, in this work, which is that we didn't, and I wish we had done this, but we didn't actually test the sampling of the softmax input, basically the logits, which would have also given us some stochasticity. That's another way of implementing sampling, which for some reason we didn't do. But essentially, if you restrict yourself to the classification output, then we have a proper representation of uncertainty in these NSNs. So it's really, this was really what really closed the loop with, and hence why I started with this talk by saying, well, we almost finished the story, was that we started from a stochastic neural network model and ended up with a plausible implementation of what this could be. Okay, so that brings me to the end of my talk. So what we've shown here is that so we can have these stochastic neural networks, both spiking and non-spiking, like they perform some Monte Carlo sampling. In the original work that we did, we tied this to the Boltzmann distribution, so we can do Boltzmann machines. Later, we did this for basically by learning the distribution itself using backpropagation. So, and then I told you about these neural sampling machines that can basically use simply multiplicative noise, only multiplicative noise and threshold neurons in order to do sampling. And that this implements inherently some type of weight normalization for free. So you don't even need to run batch normalization in your networks. And this whole thing basically does some form of Bayesian inference, as I've shown you earlier. Okay, these are the people who worked on it. So it was Giorgio was my postdoc at the time. Surov, who was at Notre Dame, but I think since then he's moved, and Greg Kalmbergs. All right, thanks for your attention.